Hi, this is Harsh, and today I'm going to be talking about LLVM, some of its design feature, and finally the LLVM optimizer. So, starting with what is LLVM? LLVM is an umbrella project that consists of number of sub-projects. The name LLVM was earlier an acronym, but now it is just a brand name for the entire project. This project hosts and develops a set of low-level toolchain components like assemblers, compilers, and debuggers. It was created by Chris Latner and now it is widely used in the compiler industry. Now, moving on to the design of LLVM, we will start with the three-phase design of a compiler. This is the three-phase design of a traditional compiler, which consists of a front end, optimizer, and a back end. The source code is fed to this pipeline, and the front end first parses the source code and generates an intermediate representation, or more commonly or more generally an AST, abstract syntax tree. That intermediate representation is then fed to this optimizer, and this optimizer can then perform a number of transformations which should eventually lead to better and faster code. That transformed IR is then fed to the backend, and this is responsible for transforming the intermediate representation, that is the IR, to target specific instructions and the code which will eventually get executed on the target machine. So this is the three-phase design of a compiler, and it separates front end, middle end, that is the optimizer, and the back end. And here is how LLVM implements the three-phase design. So LLVM consists of number of front ends for different programming languages, and it also consists of a number of backends for different targets it support. Adding a new programming language is easy. Just you need to just implement the front end for that programming language, and from there you can compile that programming language for any of the existing targets. And you can support a new target by adding a new backend in LLVM, and then you can compile from any of the supported programming languages to that target. So the front end is programming language specific, and the back end depends on the target that you want to support. Now let's talk about the LLVM optimizer and the interface to LLVM optimizer, the LLVM IR. So LLVM IR is designed to host mid-level analysis and transformations. This is the C code for which we will see the IR. This C code consists of two functions, add1 and add2. Add1 function just adds the A and B and returns the result, whereas add2 does something different. It it subtracts 1 from A and adds 1 to B, and repeats this process until A is 0, where when at that point in time B contains the sum of A and B, and returns B. So this is the IR for uh, that C code. Here we have add1 and add2, and add1 is just simple add instruction, add of A and B, and return the result of add. Whereas add2 we have three different basic block or three different blocks of instructions, where first a compare is performed between A and 0. If A is equal to 0, then the control flows to done label. Otherwise, the control flows to recurse label. In recurse, the same thing, subtraction of 1 from A takes place. Then 1 is added to B, and add 2 is called again. Basically, the repetition of same process until A is equal to 0, at which point B is returned by going through the label done. So the most important aspect of LLVM though is that it is itself defined as a first class language with well defined semantics. And LLVM is a low-level disk-like virtual instruction set. It supports linear sequences of simple instructions like add, subtract, compare, and branch. These instructions are themselves in uh, three address form, which means that they take some number of inputs and produce a result in a different register. Beyond being implemented as a language which supports strongly typed simple type systems like I32, which is a 32-bit integer, and I32 star star, which is a pointer to a 32-bit integer. And we also have I1, which is a Boolean uh, variable. So IR also uses an infinite set of temporaries to store intermediate results as shown here, temp2, temp3, temp4, and temp1 here. And these temporaries are used to pass their intermediate results to subsequent instructions. Beyond being implemented as a language, LLVM is actually defined in three isomorphic forms: the textual format that we just saw, an in-memory data structure inspected and modified by optimizations, and an efficient and dense on-disk binary bitcode format. The LLVM project also provides tools to convert between text format, the .ll file, and the bitcode format. LLVM AS is used to convert from text to bitcode, and LLVM disk is used to convert from bitcode to text format. The intermediate representation of a compiler is interesting because the IR has to be designed to be easy for a front end to generate and be expressive enough to allow optimizations to be performed for real targets. And LLVM is a complete code representation. In particular, LLVM is both well specified and the only interface to the optimizer. This property means that all you need to know to write a front end for LLVM is what LLVM IR is, how it works, and the invariants it expects. Now this was LLVM IR, and now moving on to the LLVM optimizer. And after the design of LLVM IR, the next most important aspect of LLVM is that it is designed as a set of libraries rather than as a monolithic command line compiler like GCC. LLVM optimizer reads LLVM IR in, processes it, and then emits LLVM IR, which hopefully will execute faster. LLVM optimizer is a pipeline of distinct optimization passes, each of which has a chance to process the IR and do some transformations. Common examples of optimization passes are inliner, loop invariant code motion, etc. Now each of these LLVM passes is written in a C++ file that has a bare bones structure something similar to this. Each LLVM pass is written as a C++ class, for example hello here, that derives from the pass class. Here it derives from function pass, which itself derives from the pass class. Most passes are written in a single C++ file, and this subclass is kept in an anonymous namespace so that this code is completely private to this file. For this pass to be useful, we need to pass some method of access to this pass, and for that we have a single function that creates this pass. This is the generic structure of a pass file, C++ file, and LLVM optimizer provides dozens of different passes, each of which are written in a similar style. These passes are compiled into one or more object files, which are then built into a series of archive libraries. These libraries provide all sorts of analysis and transformation capabilities, and the passes are as loosely coupled as possible. Loosely coupled means they are expected to stand on their own, or they should explicitly declare their dependencies among other passes if they depend on some other analysis to do their job. And this dependency information is used by the LLVM pass manager to optimize the execution of passes. So this uh, generic structure of a pass file contains a run-on function which is called for each function that is present in the LVM IR that is passed to this pass. So instead of printing the name of the function, here generally some more concrete code is present that performs the actual transformation. It can also contain member functions of this class which can be used to modularize the operation of pass. Now to see what exactly goes here in this run on function, we will look into LVM IR optimizations. And first of all, I must say there are a lot of different optimizations and different kinds of compiler optimizations. So it is hard to provide a recipe that will handle all the possible arbitrary problems. But most of the optimizations follow a three-part structure. First, we need to identify the pattern to be transformed. Second step is to verify the correctness of the transformation, whether it is safe to apply that transformation there. And the final step is to update the code. Now for our example, we will look at the case of arithmetic identities. So the first step is identify the pattern. And these are some of the patterns that can be optimized. So the first one is subtracting a from a, which should give a result of 0. So this can be optimized. The second one is subtracting 0 from b, which should leave b unchanged. So this can also be optimized. And the third one is multiplying c by 2 and then subtracting from that c itself. That should return c as the result. So all three of these can be optimized. So we have identified the patterns. Now the second step is to verify the correctness of the transformation. So for these the patterns that we identified, these are the uh, C++ checks for each of these patterns that matches the conditions for those patterns. So this other than this, there are some more checks related to safety of the transformation, whether or not the transformation will lead to some side effects or not. So that is also included in these checks. And after this, the final step is to update the code, and for which we need some code like this. I already mentioned that IR is sequence of functions, and each of the functions is organized as a CFG of basic block. CFG is control flow graph, and each of the basic block is a sequence of instructions. And for each of the instructions, we call this simplify instruction, which calls these checks depending on the operator. And if the transformation is valid, if v is not null here, then we replace I, all uses of I with v, and this is the update step. So the second and third step here, this code and this code goes into the run on function in the pass that we want to implement. And this this is the code, IR code, that will get transformed. So that was about the LLVM IR optimizations and how to write a pass. Not exactly, but some generic, some general approach to writing a pass in LLVM. Thanks. That was the end, and these are the references or the sources I used for this presentation.